In this video, we want to talk about finding the volume underneath of a particular surface when the region that we're considering, the domain restrictions, is not just a rectangle, that the domain is some other region beyond a rectangle. For instance, in this particular shape, if I imagine looking very high and projecting down, what I see in the domain, well, it's not a rectangle. Indeed, if I focus just on the xy plane, then what I see is that there is three different sides to this. There's the x-axis, the line x equal to 1. But then there is this curve. And by the way, this particular curve is given by the equation y equal to square root of x. So in this case, there's these three different sides, the y equal to square root of x, the x equal to 1, and the y equal to 0, or the x-axis. And so I have above this region some particular surface. So how do I figure out the volume under that surface? Now, we want to do much the same thing that we did when it was a rectangular region, namely slices. What I've done here is I've come and computed a slice when I plug in the value of x equal to 0.2. And so what I get is a little area. And this area is a function of x. And in this particular case, I've plugged in the value of 0.2. And then the strategy is that I can compute the total volume by adding up or integrating all of these little areas of all of these little slices as the x value goes from 0 all the way out to 1. For example, I can imagine the slice that happens over here at 0.5. I can imagine the slice that happens at 0.8. Let's see this example a bit more explicitly. What I have is the function 1 plus x plus y squared, and it is bounded by these three different restraints, namely that I am talking about the x-axis, the line x equal to 1, and this curve y equal to square root of x. And I'm trying to figure out the volume underneath this, and my approach is to use these vertical strips where I come along and compute the area at any value of x, and I'm imagining integrating all these values of x. That is, my strategy is to say that the volume is the integral from 0 up to 1, because I'm going to have the values of x going from 0 up to 1, of this a of x, all these little areas with respect to x. But then if I want to think about, well, what is the value of a of x? Well, a of x is an area under a curve. It's an area under a curve at a specific value of x, but then as I change all of these y values. So a of x is an integral with respect to y. So I'll put an integral sign here. I'll figure out the limits of integration in a moment. It's an integral of this function, the 1 plus the x plus the y squared. And this is an integral with respect to y. That's what my a of x is. It's changing values of y at a fixed value of x. And then you get the a of x, and you're doing an integral with respect to x. All right, so now if I want to figure out what is those endpoints, well, it starts down here at the value of y equal to 0, and it finishes up here at the value of y equal to, well, square root of x is my curve, so it depends on exactly what the value of x is. Nevertheless, what the limits of integration are 0 and square root of x. And this is kind of interesting because what it means is that unlike a rectangular region where your limits of integration were just numbers, now the limits of integration can be functions over x or y. In this case, it's the function square root of x. Now that we have this integral set up, it's just a matter of computing it. The way this works is I'm going to leave my outside integral, my integral from 0 up to 1, and then I'm going to compute the inside integral. So integrating with respect to y, 1 turns into the value of y. X is going to turn into the value of x times y. It's just a constant when I'm integrating with respect to y. And then the y squared is going to be a y cubed divided by 3. And this is all evaluated between the values of y equal to 0 and y equal to square root of x. And then finally, I'll do an integral with respect to x. So I can then evaluate what this is going to be. This is going to be, well, the integral from 0 to 1. I haven't done that yet, so I won't change it. But I'm now going to plug in square root of x everywhere. The y is going to turn into a square root of x. The xy is going to turn into, well, there's one x and then multiplied by a root x. So this is an x to the power of 3/2. Then square root cubed is also going to be to the power of 3/2, but this time divided out by 3. Plug in 0 and it's 0, 0, 0. So all of this is just integrated with respect to x. Well, now we can compute this. The x to the 1/2 becomes x to the 3/2 times 2/3. The x to the 3/2 and x to the 3/2 divided by 3, I will combine to a 4/3 x to the 3/2. So I'll put that 4/3 out the front. And then x to the 3/2, when you integrate it, it is going to be 2/5 times x to the power of 5/2. And all of this is evaluated between 0 and 1. When you plug in the value of 1, you get the value of 2/3 plus 8/15. And then when you plug in 0, you just get 0 and 0. And then indeed, if you multiply the 2/3 by 5, so you're going to get 10 plus 8 is 18 over 15, which is the same thing as 6 divided by 5. So here we have done an integral with respect to x, or excuse me, an integral with respect to y on the inside and an integral with respect to x on the outside. Let's see a somewhat different approach. Same question, but I want to do it differently. Basically, all I'm doing now is I'm doing horizontal strips instead of vertical strips. That is, what I'm considering is no longer an A at a specific X value, it's an area at a specific Y value, and I change the values of X as I go along at this specified value of Y. Other than that, the problem's the same, and my answer for the volume better be the same, but we're going to approach it in this different manner. So again, I have a volume, but now my volume, I am going to first integrate out, or on the outside, I'm going to integrate my y values. And then what I'm going to integrate is this a of y dy. Again, y is going from the value of 0 all the way up to the value of 1. So it has these endpoints, the 0 and the 1. Then I try to think about, well, what is this a of y? Okay, well, copy and paste the first integral, put down a second integral, because a of y is an area under a curve. It is again an integral, and it's an integral with respect to x. So I'll put the 1 plus x plus y squared, and this inside integral is with respect to x, and then the outside integral, as we saw before, is with respect to y. But what are the limits? What you'll notice is that on the left, it starts here, that x value, and it goes to this x value. The right one, we know this is x equal to 1 on the right boundary. But what about the left one? This is coming from the curve y equal to square root of x, but I want to know the x value, and so this is the same thing as saying y squared is equal to x. I can solve for the value of x here. So the left endpoint, so the smallest that x will ever be, is the value of y squared, and the biggest that x will ever be is equal to the value of 1. Now I have some double integral. We can go along and we can try to compute it. So this is the integral. I'll keep the outside unchanged, and I'll do the integral with respect to x of the inside. So 1 turns into x turns into x squared divided by 2, and y squared, which is just a constant with respect to x, is going to turn into y squared times x. And then I'm going to evaluate this between the values of y squared and 1. And then all of that will be integrated out with respect to y. Plugging in the value of 1, I'll keep my integral sign out the front. I get a 1 and a 1/2 is a 3/2. A y squared times 1. Remember, y is just a constant here with respect to x. So y squared times 1. So let's put in that y squared. And then I have to subtract off what happens when I plug in the y squared. So I'm going to subtract off a y squared, and then I'm going to have a y squared squared, which is a y to the 4th divided by 2, and then a y squared times y squared, which is another y to the 4th. And then all of this is integrated with respect to y. I see that there's a y squared and a minus y squared, so we can cancel that. And let's integrate now with respect to y. The 3/2 becomes a 3/2 times y. The y to the 4th over 2 and y to the 4th is just a 3/2 y to the 4th. So I'm going to subtract that 3/2. And then y to the 4th integrates to y to the 5 divided by 5. And I'm evaluating this between 0 and 1. Plug in 1 and I get 3/2 minus 3/10. Plug in 0 and I have nothing. And if I want to find a common denominator to this is going to be the same thing as 15 minus 3 divided out by the 10, which is 12/10, which is 6/5. And that's the exact same number I got previously when, instead of taking horizontal strips, I took vertical strips. So either way, I get the same answer.